All right, let's start. Welcome back to Physics 112. Let me make sure that it's recorded. I hope you had a wonderful weekend. The plan is this week we will have 3 lectures. And then next week we will have review sessions. So please do take advantage of review sessions, ask a lot of questions. Because I had to fight for it. So I want you to do well. So we will have 2 in-class review sessions on Monday and Wednesday. And then exam online on Friday. Okay. Meaning on campus. Okay. So the policy is that you can drop one of your exams. Some of you in the past took longer to learn physics. So that's the reason why I let you to drop one of your exams, the lowest one, not the first one. But the rule is, if we caught you cheating, you cannot drop your lowest exam. That's the rule. Okay. And there are other things that I'm required to do because I work for ASU. If you cheat, yeah, on campus, you don't have to be here. Yeah, but it's standard lockdown browser, those things. So, yeah. Yes. So, guys, so the rule is you cannot cheat, of course. And some of you may say like, oh, here we go again. Rizal is so full of himself. He doesn't want us to cheat. But this is actually for you. If you cut corners all the time, yeah, you can get your degree, but that habit will persist when you are in industry and maybe serve in public office. And the last thing that I want is to read news about you in the future. So it's for you, not for me. My salary is the same whether you cheat or not. Go ahead. It will be a combination of short answer, multiple answer, which is you have to pick either 1 correct answer, 2 or 3 or all of them, and multiple choice. We will not ask you to derive equations. Yeah, you and you. So yes. Zaid, do you ask question or no? Okay. All right, good. So let's start. Second is exam 1. We discussed that February 2nd. I plan to be at Caltech on February 2nd. So if you have question about exam, during the exam, I don't know, maybe I will give you 3 points. Or maybe I will be available in Pasadena. But I will not be in the room. Office hours, my first one will be tomorrow. How many of you are planning to be in my office hours tomorrow? Nobody? Only 2 of you, which is good. So we will have it in my office. If there are more than a few, then we will have it in the area outside my office in the ground floor of Biodesign Institute. And the lecture notes has been posted here. That's the QR code of the lecture notes. Should we start? So last time we discussed about Gauss's law. I hope you still remember Gauss' law. And the reason why Gauss' law is fun, powerful, and convenient, let's say we want to find a flux of a charge Q. Okay. And then we need to have enclosed area. Sorry, this one is enclosed charge. And then the area has to be a closed area. Then to find the flux, in this case, electric flux, is simply given by I'm gonna drop the perpendicular sign. I'm just gonna use cosine. And I'm gonna use, last time I used the symbol theta instead of phi, because capital Phi is the almost unanimous symbol for any flux. And this one is equal to Q enclosed divided by permittivity of the vacuum, or your textbook use this notation. Anyone still remember? Yes? So if you want to calculate the flux over this 3D surface, one route can take longer than the other route. So for example, here you have to calculate E, you have to calculate A, so 2 steps, and then you have to figure out what theta is. In the simplest case, it doesn't take that much time, but soon we will study more complex cases. Then in those cases, it's easier to just use 4 pi k and figure out what is the enclosed charge. So by enclosed charge means here, right? It's literally charge, the charges enclosed by the surface. So if there is plus q here, minus 2q here, they are outside the surface. So you don't include charges outside the surface when you try to solve the flux or the E or the electric field using Gauss's law. All right, so there are 2 examples that I put in the lecture notes. Last time we briefly discussed infinite plane. So that's the picture right there. So infinite plane, let me just use the same drawing. Looks like this. And then it has charge per unit area. So the plane is infinite, has infinity. The area of the plane is infinity. So we cannot have a charge. I mean, we cannot be exact with the charge. So charge per unit area, the common symbol is sigma. And then the question is, and then this is infinity. This is not a boundary, by the way. This is just my depiction of an infinite plane. All right. So the question is, what is the field? I don't know. R, is that R? Let's just use R. What is the strength of the electric field at this point? R from R at the distance R, perpendicular from the surface. How do you do that? So without Gauss's law, you may say, yeah, Rizal, I mean, we learn about Coulomb repulsion, then we'll just calculate all these forces. And then it will take you a long time to figure out the force here. But the magic of Gauss's law is that we can calculate the field much faster. Okay? But we have to know the symmetry. We have to know physics. So first, for infinite plane, with sigma, which is charge per unit area, we know that the field is perpendicular from the surface. The field looks like this. Okay. And then the requirement for Gauss's law is that we need closed area. Is that clear? That the field is perpendicular? The reason why it doesn't, there is no edge effect, meaning like the field should go like this. If you have a bar magnet, for example, the field looks like this. But since the plane is very large, so there is no edge effect. And then next, we can come up with a closed surface that looks like this. Right? And then we use this equation here. So let me just write it here. The flux is equal to, I hope you know this symbol, it means the sum. There are three areas, area 1, area 2, and area 3. 1, 2, 3. And then E times A times cosine theta. So area 1, let's just call the field E times A. Right? And cosine theta is equal to what? So the field is perpendicular to the what you may think surface, but we define a normal vector or surface vector. So theta here is, so the field goes like this, and the normal vector also goes to the right. So theta is 0. Theta is actually 0. So cosine 0 degree, which is equal to 1, plus the field points to the right, and the normal vector also points to the right. So this one is also E times A times cosine 0 degree, which is 1. And then the area here, what is the area 3? The area of the cylinder. It's 2 pi r times the length. So I'm just going to say A3. And then cosine theta. But the thing is, we know that E like this, right? And normal vector is perpendicular from the cylinder. So this cosine theta here is cosine 90 degree. So the whole term is 0. So this one is 2E times A. And we know that the electric flux is equal to like Q enclosed. So 4 pi K times Q enclosed. So we have 2E times area equal to 4 pi K. So what is the Q enclosed this surface? What is the charge in this area? Good, sigma A. Good job. Sigma times A. So this one is sigma times A, right? Sigma is the charge per area. The area here is the same as the area for area 1 and area 2, so we cancel. So I like to have this different angle for fun. So E equal to 2 pi K sigma. Okay. Or if you read physics textbooks, a more common way of writing this is because K is equal to 1 over 4 pi times epsilon naught, epsilon 0. Okay. It may seem complex, but this one is much faster than if you have to sum all like infinite number of vectors using each has different angles. Okay. Any questions? Good. Yeah, Natalie. Yeah, okay, good. So this one, again, this one is 3D object here, not 2D. So the field goes Okay, good question. The field goes either to the right or to the left. Right? The field, if this is the area, the field either goes to the right, towards you, or away from you. Okay. The surface is like this. So the one that, unfortunately, this one. Ugh. So here, let's say this part of the surface, the normal vector looks like this. Okay. So the angle between the field that points to the right and normal vector is 90 degrees. And cosine 90 degree is 0. Any other question? All right, so it takes a lot longer than I thought. So never underestimate the importance of practice. So I'm just gonna make a video of the second example, and I'll post it on Perusal and Canvas. Any questions? So let's recap. For Gauss's law, the electric flux is the electric fields times area, and these two has to be perpendicular. The way to address that is by adding a trigonometric function, which is cosine. And the flux is equal to 4 pi k times the charge enclosed. Okay. So let's do simple examples. So this, I think we did this iClicker last time. I may have, I think we did this last time. So the first question for iClicker, and I will give you 1 minute. What is the electric flux, which is phi E of a point charge Q? Okay. Okay, so basically all of you have answer, and I leave it open. So the answer is A. Okay. Since I said 1 minute, I'll leave it open. So the answer is A. Sorry, I have to stop this so I can grade and move to the next one. Okay. Next, we may have done this on Friday, but it doesn't hurt to do it 10 times. Okay, what would happen to the electric flux of a point charge Q if our sphere has a radius of 2r? Okay. I'll give you at least 30 seconds. And you can discuss this with your neighbor. Okay. 10 more seconds. All right. Good. Basically, 90% of you got it right. So I don't think I need to, well, let's just do it quickly. You can either do it mathematically. So let's say this is the second area. So if you do it mathematically, then you will have what, K Q divided by R square, and A is 4 pi R square. And cosine theta is equal to 1 because they are perpendicular. Or the normal vectors is parallel to the field vector. So by that, the R dependent cancel each other. Any question? Okay, so you guys ready for the exam, it seems. Okay, next, let's talk about electric conductor. So when in the first week of the class, we classify materials into 3 different types. One is conductors, second is insulators, third is semiconductor. But for this class, we can even think about or classify materials into 2, conductors and insulators. So one thing with conductors is that a lot of them are metals, or maybe all of them are metals. And then they have, some of the electrons are communal. They are shared between all atoms. Some of them are bound, but a lot of them are communal. Okay? So if this is a conductor, okay, and let's say we have electrons, somebody deposit, I don't know, 4 electrons, okay? Because the electrons can move within a very short period of time. They move such that so if they don't move, then as you can see, there is a lot of Coulombic repulsions between the charges. When I say electrons, I mean holes. Or what I mean by electron is not let's call this positive charges. We call it holes, but for this class, positive charges. So if the positive charges don't move, there are a lot of Coulombic repulsion. So what they do, because they can freely move, they move such that they minimize the repulsion. And in the end, all fields, so let's say this field is the field due to the top positive charge. This field right here is the field due to the right positive charge. And you can see the other 2. You can continue with the same mental picture. In the end, what you find is that the field inside a conductor is always 0. And another thing is, if you put more charges, they will be on the surface. Okay. So the reason why they are on the surface, because they have to minimize the energy, or in this case, Coulombic repulsion, but the charges cannot leave the conductor. This is like if your coach asks you to be in a swimming pool, then you have to be in a swimming pool. You cannot leave the swimming pool. Okay. So that's one. And then the results, the electric field inside of a conductor is 0. Okay. And then the electron, they don't move. So if you put charges in a very short period of time, they will spread out and then they don't move. So that means on the surface, the electric field perpendicular is also 0. Okay. So if the electric field perpendicular from the surface is not 0, then all the charges on the surface, they will move continuously. And this is the reason why in your textbooks it says that on the surface of a conductor, the electric field, parallel from the surface. So this is my symbol or mathematical symbol for parallel. Okay? Good. Can I erase this, or should I? Let me just erase. So let's say if there is external field. So without external field, the field inside the conductor is also 0. let's say if there is a charge nearby. So this is a conductor, a metal, and let's say there is this Q, okay? In the end, what would happen? What do you think would happen with this conductor? First, what is the electric field inside a conductor? It's always zero, okay? What is the charge distribution? So first, this, let's make it simpler. The simplest case is uniform electric field. That's the simplest case, right? So this field initially is inside the conductor. What happened if we have this, this field? This is from external field here. Okay, the field that I'm pointing here. So what happened is initially, since the charge that can move is only the electron, then electron can move to the right. And you get some positive here, or what we call holes. And then, so we have holes, let's say here, and this electron can move to the right. So basically, this chain reaction will push all electron here. And let's call it positive charges here. So initially, when the electron is here and we have a hole here, or positive charge here, then we get a small field which oppose the external field. But if we have more and more, as the conductor build up more and more negative charges, at some point the field will cancel, and in the end, the field inside the conductor is zero. So that's the underlying forces why the field of a conductor is zero. Okay. So I mean, and then there is perturbation of the field. Maybe it looks something like this. Okay. Any question? So to solve the problem, all you need to remember is that the fields inside a conductor has to be zero. Okay. You know so let's say on the exam, I may start the exam with an easy question to build your confidence. I can ask you, what is the electric field within a conductive material? So if I'm nice, this is how I would start the exam. And the answer is zero. Okay. All right, so let's test your understanding. Basically, instead of a solid conductor, now we have a donut. Let's say initially I put 4 charges here. And the question is, what is the steady state? So let me draw the donut. There are 4 donuts. The first one is like this. So this is option A. This is a free space. It's a hollow. Well, we can do it in 2D. This is a 2D object with a hollow surface. The other one doesn't change anything. The fourth one looks like this. Right? What is C? C is basically, I don't know, random. What is the answer? So I give you 30 seconds. So this is an empty surface. All right, 120 of you have answered, so maybe I'll give you 30 more seconds. What is your answer? Zaid. Ah, I see. Okay. Ah, interesting. Good. So what we discussed earlier is that in a conductor, electrons free to move, and they move such that the electric field inside a conductor is zero. So based on Coulombic repulsion, it seems that some of you answer D. Okay. So that's which a good guess. Some what 30% of you answer A, so equally distributed in the conductor. Okay. No one, well, some of you answer B, and some of you answer C. So basically, the two most voted answers are A and D. So you should remember that inside a conductor, the field is always zero. It's almost like a definition, right? So inside a conductor is here, also here, also here. Okay. And you can use Gauss's law that the field times A is equal to the enclosed charge times a prefactor. So for option A, let's say I have this Gauss's surface or closed surface. There is no charge inside, so it's good. But let's say I make a bigger closed surface like this, which is still inside the conductor. Now for option A, the charges are 4 pluses. So that means that violate, we can call it as a definition. That's violate our definition that in conductors, the electric field inside a conductor has to be 0. Let's look at option D. So for option D, if we put different closed surface, the electric field inside the conductor is always 0. But outside the conductor, the field is not 0, which is fine. It doesn't violate anything. Okay, so the answer is D. 50% of you got it right, which is pretty good. Which is high. So maybe I should make the exam harder. No, I'm just kidding. All right. Now, I have this donut. Now you don't need to look at this whiteboard. The drawing is good enough. We have a donut, and and this is a 3D object, and somehow we can put plus Q in the space inside the donut. It's not a donut really, it's a hollow sphere. The question is, sorry. Oh, you know the answer. Okay. So the answer is, what is the charge on the inner surface of this hollow sphere? Okay. Sorry for the. Oh, you need it? Huh? Ah, there's no answers. Oh, good. I forgot preparing the answer last night. All right, so everyone, just make sure you enter your answers. I'll give everyone 4 points, and I'll let it. Thank you. It took you 40 seconds to correct me. Okay, thank you. Where is the, okay, so this is the 3D hollow sphere, and you can put plus Q, and the Q doesn't have to be at the center. Okay. So maybe, you know, if I'm nice, I will put it in the center, but for the fun of it, let's put off center, put the charge off center. So we can stick with, all we know is that Gauss's law is correct. I swear by that. And then second, or we swear by Gauss's law. And then second, the electric field inside the conductor has to be 0. So how to make the electric field inside a conductor is 0? How? So we have plus Q. If there is no charge movement, then if this is the Gauss surface, what is the charge inside the closed surface? Plus Q, right? So in order to make the charge 0, then it needs to have, the negative charges needs to move to the inner surface. Some of you may think that this is the right distribution, but actually, because the charge is off center, the distribution is not going to be equal. So it's more concentrated closer to Q. And this one could just, you can view of this as Q divided by N. N is the total number of negative charges. Now, when you do different closed surface, the enclosed charge is always 0. Q minus, 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 minus. If you sum all of them, it should equal to 0. Okay, good. 170 of you already answered, so that's good. All right, the next question is, what is the total charge outside the surface of this hollow sphere? What is the charge outside the hollow sphere? Okay, first, who think that the answer is 0? You raise your hand. No. You? How about minus Q? A few. How about plus Q? Okay, good. So what you need to realize is that before the charge was 0, and then you put charge inside the space, then you bring negative charges here. That means the positive charges are outside, on the outside surface, not the inner leaflet, or, sorry, I was thinking about membrane. Basically on the outer surface of the membrane. So let's say if you make another Gaussian surface or closed surface, then the total charge inside the blue area is, so you have pluses, you have negative, and you have plus Q. Plus Q. Because this one has to match Q. And then, so you have plus, minus is equal to 0, plus Q. Okay. So this is also another demonstration, or another demonstration. Somehow the word escaped my mind, that we cannot create nor destroy charge. Yeah. Yeah. When it's, okay, so that one relates to a different problem, right? So last time, yeah, this is, it has something to do, I understand it may sound contradictory, but mathematically it's a correct statement. So this is, stems from the way mathematicians or physicists define a surface. So if this is a surface, we define a surface by two things. One is the area. Second, if we only define the area, then the surface can face, at infinite orientation, basically all Euler angle. So we define a normal vector or a surface vector, and that thing is perpendicular. So if the field is perpendicular from the surface using, daily language, it is actually parallel to the normal vector or surface vector. Okay. Any other question? Yeah. The one before is minus q. So before it was this red charges, and then the second question, which is the way I worded the question, is total charge, meaning not single charge, but if we have to sum all of them, it's plus q. Okay. I see. So using the fact that electric field inside a conductor is zero, scientists and aviation or like aeronautic engineers, they use the fact to build a safe airplane or sensitive instruments. So basically to protect scientific experiments or passengers in an airplane, they make Faraday cage. Basically, they surround the system with conductors. Okay, so that's an application of Faraday's law. Sorry, Faraday cage or conductor. And let's say if you purchase like computer, like CPU motherboard, let's say, they always ship it in what do you call that thing? Basically, conducting envelope or conducting case, not really case, conducting bag, let's say, that you can open. Okay. So I think all of these are from your textbook. If you are in elevator, the reason why the reception is bad because it affects the electromagnetic wave. Basically, it perturbs the electric field of the electromagnetic wave. That's why your reception is bad in elevator. Okay. So we have 7 minutes. Let's talk about work. I think I saw a lot of good comments on perusal. One of you asked about negative electric potential. I think another one asked about conservative force. And I trust that you understand the material. So I'll just first probably address one of them, which is conservative force. So anyone still remember what conservative forces are? What is an example of a conservative force? Yeah. Give me an example. Yeah, good. Huh? Gravity, yeah, good. Why? Yeah, because you cannot destroy gravity. So that's why physicists in the old days agree with that term. Right? And one of them that you will see is the right panel of that slide, which is electrostatic force. What are examples of non-conservative forces? Yeah, good. You guys start pushing each other. So, okay, what is a consequence of conservative forces with respect to work? Okay, maybe I need to define work in the next lecture, but we still have 6 more minutes. So the consequence is that the work for conservative force is independent of the path, right? So you can, let's say, climb a mountain and fight the gravity using different routes, different trails. And then the work that you do from physics, using physics definition, is the same. Okay, what are examples of non-conservative force? Yeah, you. Yeah, it's okay. Good, excellent. Yeah, so friction, depending on the path, you get different friction. So the work that you have, either that the surface does or that you have to do against friction, depends on the path. So that's one example. There are many aviation major here. What is another example that relates to aviation? Yeah, you, Gabe. Yeah, yeah. What is another example of non-conservative force? Relates to friction, but for airplane. Drag, yeah. So that's also depending on the path. You will have to do different amount of work. Okay. All right. So basically, for conservative force, what you can do, what you need to calculate the amount of work is just the initial and the final coordinate or state. In this case, for gravitational force, is the distance from, let's say, the center of the Earth. In this case, h, the difference is h, or position of B, which is the final position, minus the initial position, A. So explicitly, work, or W, is the kinetic energy final minus initial, all right? So this one is negative. Final is mg. What is the final position, which is B, right? Minus mass, the mass of this object, which is an apple maybe, times G times A. So this one is equal to mgh, not surprisingly. Okay. A minus B is equal to h. Okay. I think now is a good time to stop. So next time we will talk about work. Okay. And there is a perusal assignment due on Wednesday. All right, I'll see you on Wednesday. Yeah.
How we got this value for 3?
Yeah. Sigma is the charge divided by